waiting outside. Can you please? If not, we wrap up this section on energy balance by looking at how the energy balance equations change when we consider a compressible as opposed to an incompressible fluid, and we only consider the case of the linearly viscous incompressible fluid. So the basic equation remains the same. Up to this point, you can verify that there is really no distinction or no commitment to the particular type of fluid. Constant thermal conductivity, that doesn't have anything to do with whether it's a compressible or an incompressible. So that is sort of independent of the assumption of compressible or incompressible or linearly viscous or otherwise. So this will remain the same depending on the model you choose. If you adopt the Fourier's first law, which represents a linear heat conductor, which means the heat flux due to convection is directly proportional to the gradient of the temperature. Constant is given by thermal conductivity, which is you assume it to be independent of density, temperature, and so on. Then you get the Laplacian of the temperature. This we are not going to bother about. Clearly, this will change, and this will also change when you consider the compressible fluid. So when I am considering this, I am going to consider only the compressible linearly viscous fluid as opposed to the that requires a model for the stress tensor, and then I have to further say adopt compressible what type of fluid is it. And so we will take the linearly viscous fluid as an example. This, there is no need to, whatever we derive for this would be applicable for compressible fluids in general. It doesn't really have anything to do with the fact whether that might be a linearly viscous fluid or not. And so you have to see the independence of and the dependence of some of these terms. For the incompressible fluid, the T was this linearly viscous incompressible fluid. Importantly, the pressure is a mechanical variable. Now, when I write for the compressible linearly viscous fluid, have to understand or recognize that the pressure is given by the equation of state, and in general is dependent on the local density and the local temperature. They determine the local pressure through the equation of state. Right? So then let's calculate that quantity. Now, since we are going to continue to assume the stress tensor is symmetric, we have already shown that this is then given by the double dot product of the stress tensor with respect to the deformation tensor. You can easily prove it. We didn't prove it explicitly in the class. It's quite easy to prove. So now we have to apply this. We have already also seen that this would become zero for the incompressible fluid, but here we have to retain this because the divergence of the velocity field is not zero. So this we have. So then what about this? Right? So then the next quantity we have to calculate d double dotted with this, and this we saw can be written as dij. And then we want to express in terms of the second invariant. If you look at the formula for the second invariant, right? So this would be, what would be formula for the second invariant P? Yeah, half times the trace half times dii square minus. So T, the double dot product of T itself is given by 2 times minus TII squared, that is raised in the deformation tensor, that we know is simply the divergence of the velocity field. So that can be written as square. Sorry, maybe there is
The minus 250, yes.
Right? So this is what we have. So I can write 2 is equal to minus 4 times the dynamic viscosity times this, which we had, the term which we had for the incompressible fluid, that remains, right? Plus I have also square. So we can now put all of these in and then calculate that what would be double dot with what we want to calculate is I have minus P plus lambda times the divergence of velocity times I dotted with this. So I can finally gather together all the terms for a linearly viscous compressible fluid would be minus P plus lambda times another divergence of velocity, because that is I double dotted with D plus or rather minus 4 plus mu times the divergence of the velocity vector field, and so I can combine this with this and then write this as this is minus 4 mu times plus minus P plus lambda plus mu. This is what we have. This is the expression for the linearly viscous compressible fluid. So all, of course, as I've already pointed out, we will get the expression for that for the incompressible fluid invariably by simply making the divergence of the velocity of the field zero. That is fine, right? So that's one way of checking whether your results are correct or not. Important role played by the pressure, different role played by the pressure in the compressible as opposed to the incompressible fluid must always be kept in mind. Right? So let's now take the other quantity, the internal energy term. Right? So for the incompressible fluid, the density is a constant, so it doesn't influence the internal energy. Whereas for the compressible fluid, it does. Right? This will now be very similar to what we have done, what you will find in a typical thermodynamics book can now be directly applied. If you recall, there will be a problem with the notation now because I am dealing with the specific internal energy per unit mass. So typically, when you write for an expression like this, this actually refers to the internal energy per mole. This is also the entropy per mole. And this is the volume per mole. And further, right, you can also show that E can also be expressed as a function of E and P. The entropy can be expressed as a function of E and P. And then, from this, we can show that dE by dt is the specific heat at constant volume, and that dE by dV so now since I have transport phenomena would seem to do, right? So what I have to do now is simply put a star on all of this. This I'll leave it as it is. And the star would mean that I am talking about P I believe as it is, the specific point per unit mole per mole that I believe as it is. So this is what we have. A star means now what the difference here would be that since the pressure now I want to express it as rho and T. Pressure remains the same, that's the same quantity. Rather than expressing it in terms of the temperature and the molar specific volume, I would rather now want to, this is what is typically done in transport course. So I'm just assuming that, because the point is that all your mass balance and momentum conservation, they are all in terms of mass to density. So now we want to retake that, we don't want to go back and change everything to mole, which is really very inconvenient, right? So you have to make this adjustment here. If you want to borrow these relations that are available in thermodynamics, you have to recognize the difference in the notation and the units, right? So now I want P to be expressed similarly, E also to be expressed like this. So that's what I am going to do. To calculate dE by dt, I want to affect, because the variables are the temperature and the density. The densities already come with the mass balance and momentum balance. The new variable that will come, we don't want to keep it as an internal energy, right? Because the temperature is already come, it's going to come here. So the new variable in the energy balance is not going to be the internal energy, but the temperature. So we want to express the internal energy in terms of the temperature and of course the density. That's the other mechanical variable, right? And so we want this. So obviously we would want to calculate this. That's the quantity that is there in the energy balance. So I'm going to write this as dE by d rho at fixed temperature to clearly understand the context, and then this would be d rho by dt. It's coming from the chain rule actually. This is E expressed as a function of the density and the temperature, which in turn are functions of time as well as position. Sorry, that cannot be ignored. This is what it is, and the spatial derivatives are already contained in this. So I'm just directly doing the substantial derivatives. This I know already from the continuum equation. I can further express it if I want. And this I am going to write it as the spatial derivative of the temperature plus V dotted with the gradient of temperature. That I use gated, right? That we have already done in the case of the incomplete fluids. But the quantities that are of interest to me are these, and I want to relate it to the specific heat. Now per unit mass I want to bring it, and then I want to also express this in terms of the pressure and its derivatives with respect to temperature, with the density kept constant rather than the specific volume, right? So we have to now, you can easily show that V is of course inversely proportional to rho, but because the V is per mole and the rho is a mass per unit volume, you have volume per mass would be 1 over rho, right? And so volume per mole would simply have to multiply by the molecular weight, right? So this is the basic relation. It's actually fairly simple. It's only a constant that connects it's an inverse relation, but you have a constant coming into the picture, molecular weight of we're talking a single component. So there's only one component, MW refers to the molecular weight of that component, right? So let's now see. So clearly, now E, what is the relation between E, the epsilon epsilon, which is per unit mass, and the epsilon star, which is the internal energy per unit mole. Again, right? The E star is equal to what? So now I can write rho as whichever way you want to use it. What about E star? How is it related to E or epsilon? Which one we should divide by molecular weight? This is per mole. We have epsilon as per mass, right? If we want per mole, we want to multiply that by the mass per mole. That is the molecular weight. So it looks like this is what it would be. Right? So this is the basic relations that we need to use. So now let's go and calculate. So what we are really looking at is E star. E, which is what I want, is E star by the molecular weight. Right? And E star is a function of T and P. Because I know those derivatives, but actually this is fine, this is just a constant. T is fine, but I want E as a function of rho and T, so I want really this. This is really what I need. I want the internal energy per unit mass, right, expressed as the mass density and the temperature. And I have already relations for the internal energy per unit mole from thermodynamics, right, where it is expressed as temperature and volume per unit mole. So to relate the two, first I get the internal energy per unit mass by dividing epsilon star by the molecular weight, and then I find that the epsilon star is easily expressed. I can use all these relations, right, as T and P. So to get E as a function of T and rho, I need to express B as a function of rho, and that's exactly what is given here. Right? Now I can calculate the derivative. So dE by dt at rho is 1 over the molecular weight, right? So it's only with respect to temperature, which doesn't depend on the density, right? So clearly this is that's what the chain rule would give you, right? So not surprisingly, what this means is that this is CV star by molecular weight, and I simply call it the CV that we have written all along. That's the specific heat at constant volume, right? The specific meaning now per unit mass, so that's all there is to it. So I get not a surprising relation that the mass specific internal energy is derivative with respect to temperature, simply the specific heat at constant volume per unit mass. Specific heat also can be per mole or per mass. Now this is what I get. Now what about this? Is equal to, and again 1 over, so I get dE star by dV times dV by dρ. dV by dρ is simply the molecular weight minus of that by rho square. The molecular weights will cancel, so I get minus 1 over rho square. I'm going to write now dE star by dV. The dP by dt at P, and I have what I need is dP by dt at rho, and you can easily show that both are the same. Minus P. Because again that follows from the same rule. So if I want P as a function of rho and T, so I start with P as a function of T and rho. T and P, for which I have already the derivatives, and all I need to do is express B in terms of rho, right? And so when I take the derivative with respect to temperature, this is not going to come into picture at all. So you can easily show from this that dP by dt is equal to so this might seem a bit long-winded for some of you. Many of you might be able to write these expressions by inspection, but in using the chain rule and transformation of variables, I feel always as a caution that for those of us who are not so endowed with intuition, it's better to follow the transformation of variables and apply the chain rule as it is found in textbooks on mathematics and not as it is found or poorly derived in textbooks on thermodynamics. So that note of caution, but anyway, these expressions are there as I have written them. They are all correct. If you are able to arrive at them through a different route, that's fine. Right? So now what? So now I need rho dE by dt. That's the last. I'm going to write it there. Right? So that would be rho times dE by d rho at t that I have minus 1 over rho square minus t. So p is explicit in the rho and t. That's understood. I haven't written it explicit, right? But it's clear from the context. So this is dE by dE rho, constant temperature, and then I have this is still, it's going to come in a big bracket. So, and dE rho by dt, that is substantial derivative of the density, is from, it's not 0 here because the compressible fluid. I can write it as minus rho times from the continuity equation. I can write it that. And then I have dE by dt at rho. Right? So that would be Cv, where the Cv is now specific heat at constant volume, the specific heat being expressed for mass, right? Plus Cv times dE by dt. That I just leave it as it is. Right? So now this is equal to, I can assume a linear heat conductor, constant thermal conductor, because now I want to match these expressions with what I have for the incompressible linearly viscous fluid. The last term would be minus some simplification, cancellation might happen here. What will cancel out is, now if I write this, so the first term would be rho Cv dE by dt. That's what we have already got for the linear viscous incompressible. So that term is going to remain as it is. Right? Rho Cv times. I can later on write it as in terms of the spatial area. Right now I only leave it as it is. Then I have to collect together these terms. So I have here, if I look at this term, right, so that would be, there is a minus rho, there is another minus here, so those two will cancel and get plus rho, and then there is a rho here and there is a rho square here and there is a rho there, so that whole term is going to give me plus dP by dt constant rho, at fixed rho, times. Yes.
Is there a temperature T dou P by dou T?
Yes.
T term
T dou P. Where did I? Okay, it is there. plus E, that will be there. Okay, that's very true. You can't miss that. And then I have, again, these rho squared are going to cancel. So I'm looking at this term. So that could be minus P. And then there is a minus 1 over rho squared. So that is plus P. And then there is another minus here. That is going to give minus P times is equal to all of this. So clearly, the one simplification that would result is that this is going to cancel with this term. So I can now write this as rho CV finally write it in the form that would be useful. And we can take this also to the other side, right? We can take this also to the other side. So I will have minus K times, there are so many different forms of this equation, so one would have to be careful. So I have T dB by dt. So when it goes there, it will become minus T dB by dt. I just have to make sure that I put the signs correctly. Right, so would be plus lambda plus 2 then I have minus, so minus P dB by dt. So obviously it's going to be complicated. I don't know if you have the chance to use this, but clearly this is an equation. We just have to make sure we're not using what is the new variable. The variable here is a temperature. This gives an equation for the temperature, but it is coupled with all these quantities. The velocity is there, and the density doesn't explicitly appear, but the divergence of the velocity is also there, right? Which is in the continuity equation. That's no longer zero. So this is the new term that has come here, and also the lambda, right? So all of those terms are there that were not there in the incompressible fluid. Now there's another way. There are many different forms of the energy balance, so you should know for the compressible fluid. One which is written in terms of Cp rather than Cv. And that is here possible because the enthalpy can be defined for the compressible fluid, whereas it simply not have any meaning for the incompressible fluid. Are there any questions on this derivation other than few signs or a few missteps here and there? It should sort of match. This seems to be okay. So what we have, the only thing is that we should know whether we can now estimate all the terms in this equation. Velocity is a variable to be determined in conjunction with the continuity and the momentum balance. It's a variable, right? Other than that, this of course once we it can again be expressed in terms of the velocity field, right, from the deformation tensor. And then dP by dt, once the equation of state is given, I can easily go and calculate what that is going to be for the compressible fluid. So everything is determined. So now what I'm going to do is wrap up this by simply asking you to derive certain other forms of the energy balance. And to get to the expression in terms of Cp, I can use the very famous relation, which is Cp minus Cv. So this is again, I have to know that the Cp minus Cv that you found in a thermodynamics book will be the per mole, right? So that is given by minus T dP by dt squared by dP by dt. It's also written in terms of beta and the kappa and so on. Very famous relation, right? So I just want to make sure that I reproduce it correctly. This is correct. So now this is actually Cp star minus Cv star, because I'm not going to start for all the per mole quantity. over the molecular weight times this, because you have to divide it. If I divide it by the molecular weight, I'll get the per mass, right, as we have seen all along, right? So 1 over molecular weight, but here I want again the derivatives in terms of this will remain as it is, dP by dt at constant v, same as dP by dt at constant rho, and then for dP by dV, its relation we haven't quite got it, but we can easily get it here. So dP by d rho at T is dP by dV at constant temperature, then dV by d rho, which is minus the molecular weight by rho squared. So I just go and substitute it there. So minus the, I'm sorry, so dP by dV would be minus rho square by the molecular weight times dP by d rho at T. So this would be minus rho squared by the molecular weight times dP by this 1 over molecular weight, this is also 1 over molecular weight in the denominator, so they will cancel, and so I get this to be d over rho square dP by dt at rho whole square by. So I will put all of this, so we want CV in terms of CV, so CV is CV minus all of this. Right, CP minus this. So I have to here, all I have to do is to substitute it here. That will give rise to a whole bunch of new terms. Right, so that would give actually all of the terms that are there. So all I will get is I can write this from here. Later on you can Cp dP by dt minus, right, T over rho dP by dt the whole square by dP by d rho times dP by dt. Maybe I just give this as an exercise and type it out and so you can derive it. So that's how there is. I mean, I have this and then this is another term. I just have to deal with it. It's not particularly easy to use. Although books need to have a fancy for expressing in terms of the CP. Right? So that's going to be another term. But what is even more amazing is why books have a way of writing it in terms of dP by dt, and so that I will write. That maybe you can try to prove. So that's really a very confusing way of writing. I think they write it so that because the equation looks a bit more compact, so I just let you prove this. Leave it at that. So this is a substantial derivative, so I will leave it as it is. Minus plus these terms remain as they are, but there is some term here which has the dP by dt here. Those can be combined with those terms on the left hand side, and finally you can get this as that term calculated as T logarithm of rho by dt times dP by dt. Where now you have the pressure. So So this is really a compact way of writing the various terms that are going to come, because this is actually a function of rho and t. So dp by dt would further have to be, but this is not a very convenient form, because it gives the, in my opinion, it's not a very particularly insightful form, maybe a compact form compared to that. Because first of all, we have p as a function of rho and t, right? And p is not a variable of the motion. We are not looking at it as it is indeed a variable of motion, but because it's given by rho and related to the rho and temperature through the equation of state, and those are the basic variables. This gives a wrong impression that somehow we are solving for p, because actually if you want to solve the system of equations including the energy balance, mass balance and momentum balance, I have to really express this in terms of variables such as the density and temperature, and not leave it just like this. But it might be a compact way of expressing the, and again this one, right? This is really, this is actually logarithm of rho with temperature keeping the pressure fixed, right? So you just get this term, and it certainly looks more compact than if I were to consider all of these terms. But from practical point of view, this is what is given to me, and I have to evaluate it. The variables are the temperature and the density, and not the pressure, which is the equation we get if I write it as substantial derivative of pressure. So this might be a compact way of writing the energy balance, but finally we have to handle all of these terms. So effectively, we get rho times, if we want it to express in terms of Cp, we'll have to get it as Cp minus all of these terms. We'll multiply dT by dt. Further, that can be written as the partial derivative of temperature with respect to time plus P dot and then the gradient of temperature, and then you have all this stuff. So the final point I wish to make is, I think I would rather stick with this, which is complicated in itself. There's no need really to go to expression in terms of Cp, but those relations are given in the standard textbook, so you should know how they are derived. Right? So what books do also is to introduce the enthalpy, but I've avoided doing it by directly using the difference between the specific heat at constant pressure and volume. Directly have used that expression, right? Rather than introducing the enthalpy and then taking dH by dt and then defining dH by dt at constant pressure as the Cp and so on. All that is a roundabout. I can directly use the relations that are available for me from any thermodynamics text. Are there any questions? Because it's taken a while to derive this, but you should see, the difference is what I want you to see between the compressible and the incompressible, with the various additional terms that come in, the rho of Cp, and also the new terms that come in, because the divergence of the velocity is just not simply vanish, and of course the fact that the pressure is expressed in terms of the equation of state. But conceptually slightly different, other than the fact that the equations are more complicated, obviously be more tedious to solve. What is important here is to recognize conceptually what is the main difference. Are there any further questions? Okay, if not, then we'll move on to have to solve those assignment problems and probably shift it a bit down maybe tomorrow. And we'll start with the basic ideas in mass transfer. This is a somewhat new idea, but I don't want to postpone it right until the last class, so I want to introduce it, and then so that towards the end we solve all the problems in assignment 7 and 8, and whatever new problems we may introduce in this mass transfer. So the mass transfer, or the now the main point is what we see when the number of components is greater than 1. So far we have all along considered only a single component, for which we wrote the mass conservation, we wrote the momentum conservation. Of course, we have the energy balance. Now, how are these equations going to change when I have a mixture, which is typically the case in chemical engineering systems? Right? So this is an important topic, but it needs an independent course in itself to cover it in extensive detail. So let me just begin with the simplest idea, and that is a mass balance for a mixture. So when for a C equals to 1, so number of components are called as C equal to 1, we have the, I'll directly start from the continuity equation. We have this. Now a very simple intuitive way of extending this for a mixture is to recognize that now I can write a mass balance for each one of the C species. Right? So I call C species now I equal to 1 to C. Or maybe just make it alpha as the index for the components. Right? So now I can propose analogous to the pure component, I can propose that the continuity equation, this is a very shortcut way to introduce it, is equal to, but that will not be all. So when I have a mixture, I have to allow for the fact that one component may transform to another, right, through chemical reaction. So I have to account for that explicitly in the mass balance, right? If there are no reactions, then that term will simply become zero. But when you have only a single component, there is no question of chemical reaction. Even isomerization or any type of reaction means there is another component. You have to take that into account. As long as you restrict ourselves to a single component, the term due to reactions will never occur. We have to allow for the chemical transformation from one species to another and introduce it through the capital R construct alpha. That is the rate of generation, as it is often referred to, of alpha. Rate of generation actually per unit volume, rate per volume. Because everything here is mass per volume. So this will be actually mass of alpha per the rate of generation. That's a quantity that the RA, for instance, you find in chemical reaction engineering index. So this is just this, but there it is the number of moles, but here this will be the mass. So R alpha is what I have to introduce. So more revealing description of this is obtained when I look at the control volume expression. So if I now integrate it over a fixed control volume, what I will get is actually d rho alpha by dE, fixed control volume dC dV plus all over a single fixed control volume. Clearly now you can assume I can take the d by dt out, right? Because only spatial difference is a fixed control volume. So what I will get is d by dt of m alpha. M alpha is the instantaneous mass of the species alpha within the control volume. The time rate of it, that is the accumulation, can be written as, I will take it over to the other side, minus the divergence of rho alpha d alpha over the volume can be converted now into an area integral, and so I will get minus rho alpha d alpha dotted within the A over the area, the surface bounding the control volume or enclosing the control volume, plus R alpha dP over the control volume. Again, the same in minus out, accumulation will be in minus out. I am allowing for the fact that alpha can be formed. So this is the net rate of formation of alpha through chemical reactions from all others. There may be n number of chemical reactions taking place, depending on the number of species and what type of reactions are happening and so on. So this is the net generation of alpha through various chemical reactions in which alpha is included. Some it could be a reactant and it's getting converted, in some it could be formed. So this could be, you have to collect together all of them with the net rate of generation. So if this is negative, that means there is a net transformation of alpha. That is the meaning. this is the accumulation, this is the in minus out. It has a very striking similarity with the control volume mass balance for single component. There will be a rate of change of the mass of that single component. This is the net mass influx. This is the outward one of the species. There will be no generation term. So here, on top of the net influx of alpha into the system transferred across the area, in addition we have the generation through chemical reaction. It is a very simple extension. Extension for the momentum balance will not be as simple, but we will take up the further consideration of this idea in the next